Hi there, thanks for joining us. This is a Q&A edition of Space Nuts. My name is Andrew Dunkley. Thanks for your company. Coming up, we're going to answer audience questions. One from Ken. I'm going to paraphrase his 500,000 word question by saying, why don't the numbers add up when turning hydrogen into helium? Also a question from Mark about caves on Mars. And Casey wants to talk about changes in stars. That's all coming up on this Q&A edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
I just got a text to say my car's been serviced, so I'll be back in about 20 minutes if you just want to hang on. No, I'm kidding. Joining us to answer all those questions is Professor Jonty Horner, Professor of Astrophysics at the University of Southern Queensland. Hi, Jonty.
Good day. How are you going?
I am all right. Good to see you again.
It's good to be back. I was going to say, the amount I've been talking too much, you've probably got time to go and get the car and...
I could probably ask you a question, bolt down and get the car and come back just in time to hear the end of the first sentence.
Yes, and no, I do apologise to listeners if I've rambled on too much, but it's when you get to talk about your hobby and people have to listen. It's, hard not to get excited and...
It is, isn't it? It is. Let's get straight into our first question. Hi, Andrew and Jonty, I'm going to say. It's not what he wrote, but anyway, it doesn't matter. Ken from Maroochydore, long-time listener and fan, and love the way you make complex issues sound simple. I am trying to understand the basic fusion reaction that both me and my accountant are struggling with. The basic fusion reaction in our sun converts hydrogen to helium. To summarise the reaction, 4 hydrogen nuclei, that is 4 protons, go through 2 steps to create 1 helium nucleus containing 2 neutrons and 2 protons. Additionally, gamma rays, neutrinos and positrons are released. My anatomy textbook tells me that about 600 million tonnes of hydrogen convert to 596 million tonnes of helium every second. The 4 million tonnes is conveyed to energy as per E equals mc squared. If neutrons had a lower mass than protons, it would all make perfect sense, but they don't. They have a higher mass. So the mass of the helium nucleus is higher than the mass of the 4 protons. All the explanations I've read sound pretty dodgy, and my accountant says he could never get away with such explanations with the tax department. Could you please explain the devil in the detail that I'm missing? I love it. That's a great question. And thanks for the research, Ken. Hope all is well in Maroochydore. Not far from you, just a bit further up the coast.
Yes, out to the coast and up a bit north of Brisbane, up on the Sunshine Coast, which is kind of a lovely area. It's kind of...
It's only kind of lovely.
Yeah, only kind of lovely. It's getting very aggressively more and more touristed. Attracts a slightly different tourist demographic to the Gold Coast, which is south of Brisbane, but is still a little bit more touristy than you'd like it. It's a little bit like hippie central, but not to the level of Byron. That's
I get you. Yeah. Byron is the hippie capital of the country, I think.
Yeah.
Or to be more like Nimbin, a bit further down. That's very, very hippie. Anyway, so yeah, he doesn't understand the balance. It doesn't. To paraphrase, why don't the numbers add up when turning hydrogen into helium? That's the short version of the question.
And I totally get that, because if you look at the masses of protons and neutrons in isolation and add them together, helium is 2 protons, 2 neutrons. Add them together, taking the mass of a proton and the mass of a neutron, and you get a given value for the mass of a helium nucleus. And then you look at the mass of a helium nucleus, and it isn't that mass. And that doesn't make sense, because if you've got 4 nucleons together, surely the mass of the nucleus is the 4 nucleons added together. And that's effectively the fundamental of what's being said here. Added to which, a hydrogen nucleus is a proton, a deuterium nucleus is a proton and a neutron, but a hydrogen nucleus is a proton. 4 hydrogen nuclei go together to make a helium nucleus, which is 2 protons, 2 neutrons, and in the process you kick a few things out and do a few weird things. Surely, therefore, 4 hydrogen nuclei have the mass of 4 protons. 1 helium nucleus has a mass of 2 protons plus 2 neutrons. And when you get the numbers off Wikipedia, that would suggest that the helium nucleus should be more massive than hydrogen, and you should lose energy rather than create it. because you've had to create mass, fundamentally. In actuality, though, the mass of the helium nucleus is lower than the mass of 2 protons plus 2 neutrons. And that's where the misunderstanding is coming in, or not really misunderstanding, that's where the complexity and the confusion comes in. And takes everybody a little bit to get your head around this when you first come across it. Helium nucleus, quite rightly, is made of 2 protons and 2 neutrons, but those 2 protons and neutrons are held together. They're bound together by the nuclear force, held in strongly enough that the repulsion from the 2 positively charged things don't blow it apart. So there is something going on called the binding energy. And the binding energy is the amount of energy you would have to throw at a helium nucleus to separate the 2 protons and the 2 neutrons and make them fly through space separately. Again, with the energy and mass equivalence, if you were to do that, you would then have 4 nucleons independently of each other, which would have the mass we've just calculated, but you've had to add energy, and energy is equivalent to mass. So what it's saying is that the mass of a helium nucleus is lower than the mass you would expect from the 4 nucleons because of the effect of this binding energy that's in there. And that binding energy is something we can calculate. Helium is remarkably high compared to the things on either side of it, helium-3, hydrogen-3, lithium, and that. It's incredibly tightly bound. That binding energy is what leads to the little bit of mass deficit with the helium atom being lighter than the 4 nucleons that went to make it. And it's that energy that's released. Now, this is why nuclear fusion can work, because if you put 4 nucleons together from hydrogen atoms and from hydrogen nuclei to make a helium nuclei, with the binding energy, it means you get more energy out than you get in. You produce energy. And that's true if you fuse helium. Helium is difficult. You can't fuse it to anything until carbon because lithium, beryllium, boron have a lower binding energy per nucleon than helium does. So you actually have to put energy in to fuse helium to those things rather than getting energy out. So that doesn't happen. Helium can fuse to carbon, but you need 3 helium nuclei to collide at once, which is hard. From then on, from carbon upwards, you can get a little bit of energy out from fusing heavier and heavier things together until you get to iron. Iron 56 has the highest amount of binding energy per nucleon. So if you try and fuse iron atoms to make a heavier atom than iron, you have to put more energy in than you get out. And that's what causes stars fundamentally to go supernova, is that they fuse heavier and heavier things to iron and then the fuel source is cut off suddenly. They then collapse, you get a boom because of the shockwave going bouncy, bouncy. Some of the energy from that supernova gets taken up in the fusion of iron to make heavier elements and gets sunk into that, which is where we get all the elements heavier than iron, everything up to uranium and beyond. Those things heavier than iron, the binding energy per nucleon gets lower and lower the further up you go, which is why for things heavier than iron, nuclear fusion costs energy, but nuclear fission liberates energy because you're going back up the slope again. So uranium fissioning to become lighter elements gives off energy because of that binding energy difference. It's all part of the same thing. Now, I understand that intuitively this really isn't a satisfying answer because this binding energy sounds a bit like your accountant thinking you've got a tax dodge. It's a bit like capital gains tax or fringe benefits or what is it, negative gearing. Binding energy may well be the negative gearing of the cosmos because it's when you put 4 nucleons together, they weigh less than they would do on their own. It's the ultimate waste loss plan. But it is this binding energy that leads to the mass you would measure for a helium nucleus being less than the mass you would measure for 4 hydrogen nuclei. And it's the masses you measure, not the masses of the individual components if you took them out and put them on their own, that is the important thing. This is usually skipped in the explanations, and this is where the challenges come in. Because in the explanations you just say, a helium atom is less massive than 4 hydrogen atoms, ergo, some mass has been lost, therefore energy is produced by equals mc squared. And it skips all this discussion of the particle physics underpinning it and this binding energy. As always, there is a fairly detailed discussion of this in the Wikipedia page for helium-4, talking about the stability, and that's got the binding energy curve in. There is also discussions of binding energy and that out there, and particle physics out there. It is basically, though, that the binding energy causes this mass deficit, and it's that mass deficit that has been converted to energy that is then liberated in fusion. So I appreciate it is not the most satisfying answer, but that's our understanding of the why behind all of this. And the proof is in the pudding. Fusion happens. It produces energy at the right level that we calculate that all of our models suggest it should do. So it seems that this is a very accurate representation of how the world works, even if it doesn't immediately feel satisfying and commonsensical. And part of that is that common sense we've developed based on the experience of the world around us at our scales, at macroscopic scales. And the further you go from the conditions in this room, the less accurate common sense is at predicting the outcomes of things. And that's why it's hard to work these things out.
Yeah, it's like, I mean, listening to your explanation would be the same as me trying to explain to a kangaroo how to use a pedestrian crossing. Yeah. So, you know, it's, I can understand Ken's frustration. But if I understand your explanation thoroughly, Ken, what Jonty was saying was that shift happens. That's basically it, I think. But thanks for the question. Great to hear from you. This is a Q&A edition of Space Nuts with Andrew Dunkley and Professor Jonty Horner.
Roger, you're loud and clear here also.
Space Nuts.
Okay, Jonty, our next question says, Fred was talking about caves on Mars, and that got me thinking. The caves on Earth are primarily made of limestone, which has high concentrations of CO2 that was locked in by millions of years of sea creatures popping into the sea, creating a layer on the seabed that could be seabed. Could it be the same effect on Mars? No punctuation, caught me out there. If so, I need to ask the question you get. If so, I don't need to ask the next question. You get what I mean. But the next question is, if caves are deep enough, could it be possible that the atmosphere at the base of these caves could be dense enough to create a stable atmosphere with higher concentrations of oxygen for life? And could that life be looking at Earth with envious eyes? Yeah, very funny. Hope not. Mark. Thank you, Mark. So caves on Earth, not all of them, but quite a lot of them are limestone. Could it be the same way as caves were created on Mars? I think that's the initial question.
So I'd stress here I'm not a geophysicist, but the limestone we get on Earth is stuff that is now above sea level that was once below sea level. You had all these calcium-shelled creatures die and fall to the bottom of the ocean and then get compacted over millions of years to form this rock, and then plate tectonics lifted the rock above the surface of the ocean. I guess on Mars you'd probably argue the oceans went away. There's not plate tectonics to lift things up, but the places that were ocean now no longer are. This is predisposed on the idea that you develop things with enough calcium to be able to make shells and stuff like that. I believe, and I stand to be corrected on this, that the things that use calcium are typically oxygen breathers, not carbon dioxide breathers, but I may be wrong on that. They die, they precipitate stuff out. Now, the first point is whether there could be limestone caves on Mars. Now, that would be predisposed on the appropriate evolution of life to get to the point where you had things that could leave fossils, that could leave shells and stuff. And we haven't yet found any fossils of such life on Mars. And without such life, you couldn't get the limestone. I think will be an open question. I suspect if we got Earth scientists and stuff like that in on the show, they'd have good reasons why limestone would be unlikely to be common on Mars, because yes, you did have oceans and lakes, but was there enough time for enough deposits to be made of shelled creatures, which we don't even know evolved? So there's a lot of complexity there. It's obviously something I don't know for definite whether you could have limestone on Mars. I haven't heard of it being detected on Mars, but absence of evidence is not evidence of absence. But I don't believe it is common, otherwise we'd be fairly well aware of it. But there are other ways you can get caves on Earth. And I mean, we've got lava tubes and lava caves up in North Queensland in Ulladulla. We've got similar things have been found on the Moon and Mars. There are skylights and lava tubes on Mars that people have even suggested could be suitable places for humans to go and live, because if you're underground, you're shielded from radiation. And of course, if you're in a cave, you can seal the entrance and fill it with air. which would be good. Now, that kind of links to the second part of the question here from Mark, which is if you have caves deep enough, could you have enough atmosphere in those caves to have atmospheric pressure? I think that's unlikely here because those cave systems would probably be connected to the surface and air would diffuse out of them. So you'd equilibrate. And you don't go into the cave in the lava tube on Earth and suddenly it's 3 atmospheres, because if it was 3 atmospheres, the air would be pushed out through the entrance. So I don't think you get to atmospheric pressure in these caves unless they were very, very deep and were sealed, and the air was sealed in from when the atmospheric pressure was higher and it hadn't escaped. But with the porosity of the rocks, I think that would be very unlikely. The next thing is about there being oxygen in those caves. And I think of all of these things, that is the least likely because Mars doesn't have much, if any, free oxygen in the atmosphere because oxygen reacts with everything. And on Mars, there are bits of methane being produced. We're not quite sure what's going on there. But the oxygen, free oxygen from Mars has been very effectively absorbed into the surface through chemistry. Big part of why Mars looks red, of course, is that you can effectively say the surface is rusted. Iron oxide. The oxygen in the air has reacted with the iron in the surface and been locked up.
Like a lot of Australia.
Yes. Now, you can produce some oxygen in Mars's atmosphere if you get water into the atmosphere, and there is a very small amount, traces of water in Mars's atmosphere. We do get water clouds there. Without an ozone layer, some of that water, particularly the water that gets highest in the atmosphere, will get dissociated. It will get broken into hydrogen and oxygen by ultraviolet radiation, and the hydrogen will then escape because hydrogen atoms travel so quickly that Mars's gravity can't hold them, which means the hydrogen goes away and the oxygen is left behind. So you will be producing small trace amounts of oxygen in Mars's atmosphere all the time, but then that oxygen would then be used up in chemistry and removed. So in order to have large amounts of oxygen in one of these caves, you'd need a source of oxygen. And you'd need that source to provide enough oxygen that oxygen can overcome everything that's trying to remove it. Now, on Earth, it took a huge fraction of Earth's life before you got the great oxidation event for life to actually get to the point where it could produce more oxygen than the Earth system could absorb. So to have abundant oxygen on Mars strikes me as very unlikely. It may be possible that in the future that'll change, though, because if we went to Mars, then one of the ways people are thinking the first human habitats will be built will be to go to the caves in the lava tunnels and live there. And then you can make a sealed environment that you can then pump with an artificial atmosphere. So it could be that if you ask that question in 20 years' time, Mark, the answer would be yes, there are caves with high enough atmospheric concentrations for life. We've put them there. Would they be looking back at Earth with anxious eyes, with envious eyes? I guess it depends on the person who's emigrated there. There's these fabulous ideas of what humanity will look like when we're a multi-planet species. But the thing that stuck with me more than anything else was this amazing talk from a doctor in 2012, 2013, 2014 at one of our space research conferences, who basically talked about the difficulty humans have reproducing when you go even very slightly away from standard temperature pressure at sea level. Talked about the challenges that the invaders had into South America when they reached the high Andes. They couldn't colonize there because they weren't able to reproduce. Talking about very slight changes in conditions being enough to render our ability to have children null and void. On Mars, you've got 1/3 gravity. Unless you get dystopian science fiction future where women enter centrifuges for 9 months in order to carry a child to term, in order to simulate 1G, the perspective is that at least in the relatively near future, humanity on the moon, humanity on Mars will be not self-sustaining. We won't be able to have children there. So it may well be that Mars becomes a interplanetary retirement home. People sow their wild oats, live their lives, and then go to Mars later in life for the adventure. And then would they look back with envy? Well, they'd probably look back with a little bit of longing, but also they'd have the excitement of where they are. So it could be that in 20 years' time, 30 years' time, there will be life in the caves with artificially enhanced oxygen levels, looking back at Earth, watching the news and all the rest of it. But I don't think at the minute that that's the case.
Okay. Fair enough. And just one more point, Mark. I just did a quick search about could there be limestone on Mars, and according to an article in Science Daily, which dates back nearly 20 years now, yes, limestone, specifically carbonate minerals, likely exist on Mars, but probably not in massive, thick sedimentary beds found on Earth, while early Mars was warmer and wetter, supporting the potential for carbonate formation. The planet lacked the extensive oceans and tectonic plate activity required to build large limestone deposits. So there you are. They think there possibly is limestone on Mars, but not enough to do what we've seen on Earth. But great question, and certainly food for thought, and appreciate it, Mark. Thanks for sending it in. This is Space Nuts. Andrew Dunkley here with Professor Jonty Horner.
0G, and I feel fine.
Space Nuts.
And you're listening to a Q&A edition. We've got one more question to tackle. Hello, this is Casey from Colorado. She's one of our regular contributors. I have some questions about stars. Why do the activity levels of stars change? What causes solar cycles? Does every type of star go through solar cycling? Love the show. Hope you're both well. Thanks, Casey from Colorado. It's a good question because we don't really talk about this sort of thing much, but we're just about to go out of the peak of solar activity in our own solar system, the 11-year cycle that they talk about. So that's probably where we should start. We know the sun goes through an 11-year cycle, and and we witness different things during those 11 years because it's constantly changing.
Yeah, it's worth stressing straight up that effectively all stars are inherently variable to some degree. And our sun is actually incredibly low variability compared to many stars. The solar cycle we observe is arguably a 22-ish year cycle with 2 peaks and 2 minima. And the subtlety there is we get solar maximum when there are lots of sunspots, lots of activity, more aurora, and solar minimum when we've got fewer sunspots, less activity, fewer aurora. And we get those on and about an 11-year cycle from one peak to the next, sometimes a bit shorter, sometimes a bit longer. But the origin of the solar cycles with the sun is the sun's magnetic field. The sun has a magnetic field that runs from the North Pole to the South Pole, and it rotates in such a way that the rotation period at the equator and the rotation period at the poles are different. It rotates as a fluid body. So the time it takes the sun's equator to rotate is a couple of days quicker than the poles. The magnetic field lines running from the North Pole to the South Pole get hooked up in the material and gradually get wound up a bit like an elastic band. And so the sun's magnetic field gets more and more complicated through the 11 years, starts to get kinks, and the kinks break through the surface. So you get locations where the magnetic field comes out of the surface, loops up and goes back down. And in the places where it's nearly vertical, it cools the surface of the sun because it suppresses convection of new energy from underneath, leading to cooler spots which look darker and therefore are sunspots. And gradually the sun gets more and more wound up. Sunspot activity begins at high latitudes and works its way down towards the equator. And eventually around solar maximum, you get the field lines starting to snap and break, and you get a polar reversal happen. The North Pole becomes the South Pole, and the South Pole becomes the North Pole, and then it all begins again. So the reason we talk about a 22-year cycle is you get solar maximum with North Pole to the north, well, North Pole to the top, and then a minimum, then solar maximum with the South Pole to the top, then a minimum, then you're back to where you started from, roughly. Those cycles are driven by the magnetic activity of the sun, and they vary the brightness of our star by a vanishingly small amount. It's an incredibly stable star. I think you're talking about variability on the level of about 1 part in 10,000. Something like that. Now, that is such a low level of variability that if we were observing an other star, we probably wouldn't be able to pick up the variability in the total brightness, but we would be able to pick up the magnetic activity. And this is magnetic activity in star spots are one of the challenges for people trying to find exoplanets, because a star spot can mimic as an exoplanet, and stellar activity like the sun's magnetic cycle and the star spots that go with it can actually mimic a radial velocity planet. So there's a lot of work done in when we think we've got a signal confirming that it is actually a planet and not a star spot. So you've got that kind of stellar activity. Now, most stars are significantly more variable than the sun, and there's a lot of other ways stars can vary. We think that most sun-like stars will have sunspot cycles like the sun, and it's due to the structure of the convective and the radiative zones and all the rest of it, the internal structure of the sun. A bit like the Earth has a crust, a mantle, and a core, the magnetic field in the top layer of the sun can get tangled up. Stars of different masses have a bit of a different structure, but there's a lot of other ways that stars can be variable, and so we have a very wide variety of different types of variable stars. There are flare stars like Proxima Centauri, which have stellar activity that can occasionally be a super flare that can cause a star's brightness to change by almost a factor of 100. And I normally talk about Proxima Centauri being 100 times too faint to see with the naked eye, but in one mega flare it had a few years ago, it almost reached the edge of naked eye visibility. That flare was that intense. You've then got a large number of stars that vary in brightness because they pulsate, because their size changes fundamentally. And usually these are stars coming towards the end of the life, entering a bit of instability for various reasons. Some of them are only just moving off the main sequence or are very young. Others are supergiant and giant stars with different kinds of variability. But that variability causes their diameter to change, causes them to pulsate, and that's because they're just slightly out of equilibrium. When they're at their smallest, they get hotter. They're putting out more energy because they're a bit hotter. The surface layers, therefore, are pushed outwards with more force than gravity can push them in, and they start to expand. They go through the equilibrium point, but because they're still expanding, they keep going. As the star's outer layers get bigger and bigger, the star cools, because when you take a gas and you increase its volume, you lower the pressure and you lower the temperature. So that material cools and eventually is giving out less energy than gravity pulling in would cause, and it starts to collapse again. So instead of, like the sun, staying at that very fixed radius because gravity and radiation are balanced perfectly, you can get this oscillating behavior where you overshoot in both directions. And sometimes that's fairly small, sometimes that's fairly large, and it happens at different phases of stars' lives in different ways. One of the most famous types of variable stars are known as the Cepheid variable stars. And these are somewhat evolved stars coming towards the end of their life, where the pulsation period is directly linked to how luminous a star is. So two similar stars, but one's brighter than the other. Intrinsically, you put them at the same distance, one's more luminous, looks brighter. They will pulsate with different periods, and if you can measure the period, you can measure how luminous that star is, and that makes Cepheid variables an excellent step on our distance ladder. Because you see a star that's a certain brightness, you don't really know how far away it is. But if you can measure the period of the Cepheid variable pulsating, that tells you intrinsically how luminous that star is, which means we can work out its distance. So they're really useful. Some stars are astonishingly variable. Among the stars with the biggest variation in brightness from brightest to faintest are known as the Mira stars. Mira, the archetypal one, is known as Mira the Wonderful. Mira, at its brightest, is easily visible with the naked eye. At its faintest, you need a telescope to see it. And a few of these stars have amplitudes, the difference in brightness between the brightest and faintest, that are such that they vary in brightness by more than a factor of 10,000. Couple of examples here. Chi Cygni, which at its brightness is a magnitude 3.3 star, so comfortable with the naked eye but not that bright. At its faintest is magnitude 14.2. That is a factor of about 25,000 in brightness between brightest and faintest. That is so long a period that was discovered, that variability, back in 1686. You've got a wide variety of Mira-type stars dominating the stars with the biggest variability, but there are other type ones in there. Our Corona Borealis is a famous one in the bowl of the Northern Crown, normally only barely visible with the naked eye. It's a carbon star, where the Mira stars have a periodic variation. They're pulsating in a broadly periodic way with periods of a year or more. Our Corona Borealis is different. It shines along, and then suddenly it's like somebody drops a curtain in front of it and its brightness plunges, and then it gradually brightens up again, and that is not exactly periodic. It's known as a carbon star, and what's happening is that occasionally it's got a huge amount of carbon in its atmosphere. Occasionally the carbon condenses into soot, blocking the light from underneath. That cools the outer layers, which gets this runaway condensation of carbon into soot. That traps the radiation from inside, so the heat builds up inside until eventually the carbon gets turned back into a gas again, the clouds clear and the star brightens again. So
I was just going to stupidly suggest that it was soot.
Yeah, and it is. It's a carbon star. And our Corona Borealis is the archetypal most famous one. It's described as a low-mass yellow supergiant. So again, it's a star coming towards the end of its life. Every so often, can be after just a few months, or it can be a few years, it can dim by as much as a factor of 10,000 because it kind of soots up, clouds up. And if you look at the light curve of that, if you're bored, have a look at the light curve on Wikipedia, because it's really head-scratching, and it shows you how random this is and how hard it must have been for people to understand. There was an incredible deep minimum that happened in the mid-2010s, I think it was, where it dimmed and then it stayed dim for ages. Normally it's bright and then it dims for a bit and then it brightens up fairly quickly. But fundamentally, there's a huge variety of ways in which stars can vary intrinsically themselves. Their brightness can vary. It is known from discussions with the traditional owners of the land here in Australia that the variability of Betelgeuse and Aldebaran, two bright red supergiant stars in our summer sky, northern hemisphere winter sky, are variable. We saw that with the great dimming of Betelgeuse about a decade ago now. That kind of variability has been known for hundreds, if not thousands of years among traditional owners around the world who look at the night sky. So that star's varying intrinsically in brightness, the star itself varying. And it's a wonderful rabbit hole for people to wander down. It's another area of astronomy where amateur astronomers contribute a lot, because there's very active variable star observers who will go out there and measure the brightness of stars repeatedly to track when they vary. We get a lot of that knowledge. You've then got a second type of stellar variability, which is not intrinsic but is extrinsic. What I mean by that is an intrinsically variable star is the star itself changing. An extrinsic variation is something else causing the brightness of the star to change. You know, put your hand in front of the star's disappeared because your hand's absorbing all the light, it's disappeared. We have multiple star systems where we have eclipsing binaries. Algol is possibly the most famous of these, the winking demon star, whose brightness drops by about a factor of 3 every couple of days. And that star is bright enough to be easily visible with the naked eye, and the variability in its brightness is sufficiently large that it's easily noticeable with the naked eye. So its brightness varies, I think it's every 70 hours or so. I just want to check it out. No, it's less often than that. Algol's brightness varies every 2.86 days. So every 2.86 days, the brightness of the star drops from magnitude 2.1 to 3.4. That's a brightness change of about a factor of 3 times, roughly. And it dims for about 10 hours and then brightens up again. Became known as a winking demon star. That has been known to be variable since prehistory in reality. There's allegations that perhaps an Egyptian calendar that talked about unlucky days may have been linked to that. That's questionable. Where it is really interesting, though, is the variability of Algol was first explained by John Goodricke, who is one of those heroes of astronomy you don't hear about very often, mainly because he lived a very short life. He presented findings in May 1783 to suggest that the variability, the periodic variability of Algol was caused by a dark body or a dimmer body passing in front of it every 2.86 days. He was awarded a medal for this. I believe he never got to receive the medal because he died, as I say, very, very young, died at the age of 21, got the Copley Medal in 1783. I think he was passed away 3 years after that. So in just 21 years old, he contributed hugely to our modern knowledge of variable stars. And, you know, it's very unfortunate that he passed away at such a young age. But he was able to explain this variability that had been clearly known for a very long time. It's obvious to the naked eye that this star gets dimmer. It's not a subtle effect. But he was the one who was able to explain it. Despite his challenges, he was someone with certain physical disabilities. He was someone who had a very difficult life. But he had such a visionary intellect at the time to come up with the explanation that this periodic variability and the style of it and the frequency and the depth of it being so repeatable was because this was actually two objects going around each other. Ties in with the exoplanet chat we had earlier, because in a way, this is the indirect discovery of the binarity of Algol. You don't know that there are two stars there because you see two stars separately. They're so close together, you can't separate them with telescopes, modulo hugely massive interferometers we have today. But you can infer there are two stars there by the extrinsic variability, the variability of the light we receive because one blocks light from the other, fundamentally. So that also causes cyclical variations in brightness, but it's not the star in this case varying. It's the result of the environment around the star blocking some of the light.
Yeah, okay. So the answer to Casey's questions are fundamentally yes. most stars probably have some sort of variability, some more than others. The solar cycles are caused by the buildup of activity.
Yeah.
And does every type of star go through solar cycling? Probably.
Does it? It's like I said, it's one of the big challenges for us with our radial velocity work, looking for planetary stars, is filtering out the stellar cycles, and that's particularly a problem for finding planets like Jupiter on a Jupiter-like orbit. Jupiter goes around the sun every 11.86 years. The solar cycle is about 11 years. It's hard to disentangle the two. There's also a fascinating branch of science, and one of my colleagues at UniSQ is one of the world's experts in this, Professor Simon Murphy. This is a discipline called asteroseismology. We know about the Earth's interior because of earthquakes. We can figure out the crust, the core, the mantle by how different types of seismic waves pass through the Earth's interior. So we'll listen to the Earth ringing like a bell after an earthquake, and we can use that information to sense what the interior structure is and how it varies. The science of asteroseismology is doing the same kind of thing with stars, looking at how they wibble and wobble to map out their interior and understand it, and that's fundamentally tied to the variability. Now, Simon's got a couple of PhD students working with him and doing some fabulous work, including a guy called Tom Love, who's down in New Zealand, who's an amateur astronomer there doing a PhD, just finishing up with us, where they're looking with Simon at these asteroseismology wibbly-wobbliness and also at the variability of stars, looking at a group of stars called the Delta Scuti stars, which are a particular type of oscillating, varying, vibrating star, looking at how their interiors behave, looking at how old they are, so we can better understanding of the physics going on and a better understanding of where these stars sit in the story of stellar lives. So this kind of question is one that leads to whole rafts of amazing science that's been done. And I think, like everything we discuss on the show, these questions are all entryways to rabbit holes that can go as deep as you want to.
Yes, absolutely. There you are, Casey. Thanks for the question. Really, really interesting. And it's fascinating stars. I've been spending a lot of time outside with my telescope recently and photographing where I can some of the big stars that are visible. I think did I get Sirius recently? I can't remember. I've got a couple of good ones. I got Alpha Centauri the other night, which turned out really well.
Yeah.
But thanks for the question, Casey. If you have questions for us, please send them in via our website, spacenutspodcast.com, and click on the Ask Me Anything button at the top. It's labelled AMA. You can leave text or audio messages. If you've got a device with a microphone, you're all set, such as cell phone, mobile phone, tablet, anything like that, or your computer. They've got built-in mics these days, and just tell us who you are and where you're from, and we'd be happy to try and solve your riddles. And have a look around while you're there. Check out the shop, check out Astronomy Daily, maybe sign up for your daily feed of astronomical news, and click the supporter tab if you'd like to help us out. That is totally optional. And thank you, Jonty, for all your help today.
Absolute pleasure. It's always good to have a chat.
We'll see you soon when we talk astrobiology part 2. That is Professor Jonty Horner from the University of Southern Queensland. And thanks to Hugh in the studio. Couldn't be with us today. Hugh, he's an ex-radio guy, so he thinks he's a star, which means his equator rotates more than his north and south, and he's back in hospital with a twisted bowel. And from me, Andrew Dunkley, terrible. Thanks for your company. We'll catch you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.